Okay. Hey everyone, welcome to the Boiling Point series presented to you by yours truly seniors. I hope I am audible. If not, just let me know. We'll start off with the Foundations of the Data Science series exam crash course. And on today's agenda, we'll be starting off with the requested concepts from your end based on the Google Forms that were circulated to us. And after which we will be taking up the previous year question paper, how to attempt it, which diagrams to use where, how to answer crisp and clear so that you can have all your mark scoring answers ready. After which we'll take up your tricky questions that we have solved in our previous year paper solving sessions, and we'll just take it forward using like whatever materials we have prepared for you guys, and then we'll conclude the session, after which we'll be sharing something like a digital space where you can answer and you can ask questions, and we will solve your doubts and everything. So that is the basic agenda for the day. So we'll just start off with the requested concepts. This is just a brush up session so that you guys can familiarize yourself with the core ideas before we dive into solving questions. And the concepts that we'll be covering today is uh, first, visualization, that is your box plots and violin plots, when to use which one. Then your feature selections, your filter and your wrapper based methods, your perceptron, linear and logistic regression. So all of these will be covered under the particular requested concepts part of the session. So we'll just start off with the requested concepts. Okay. So first we'll start off with the box plot. I hope it is visible. Yeah. So your box plot is just another visualization technique which will help you to see your distribution of data using like these five numbers, which is really important, which is your minimum, that is in this extreme end, your maximum, and your Q1, Q2, that is your 25%, your 75%, and your 50%, that is your median. This line in between is your median. This is your Q1, your Q2, and this is also known as your interquartile range. The speciality of this particular graph is that you can see that there are these dots, right? These are your outliers present in data. Sometimes when you have outliers, they throw off your distribution when you're not scaling or standardizing them properly according to the models in which you will use. Now, this is basically your whiskers, which will extend to your minimum and your maximum, which excludes your outliers. And again, this box is your interquartile range from Q1 to Q3. This contains 50% of your data. Your strengths of this particular graph is that it has like a quick summary. It is really easy to compare multiple distributions, but the limitation is that it kind of hides the actual shape of your distribution. So now the thing is, over here you can see that even though you have different modes present here, it's a bimodal graph. It almost like just represents or like resembles your uniform graph. And when you're trying to make out what distribution or the shape of the graph you're getting with respect to your distribution, you will not be able to make out when it comes to box plot. So that's a disadvantage, and that's the main reason why we use violin plot also. So this is your violin plot. What it shows is basically your box plot plus your density plot. It's just a rotated and mirrored version. The width is basically nothing but your frequency of data at that particular value. And again, since it's a mixture of your box plot plus density plot, you can see that it contains the information that your box plot would also present, like your interquartile range is present, your median is present, and you can see all of that information right here also. It also shows like your shape of the distribution of the data. For bimodal, you would literally have two bulges clearly visible. For your uniform, even though like at this point it's like it'll almost represent a rectangular shape. For your normal distribution, it would be just like your ellipsed shape. So that is like your violin plot put into one particular part. And based on your distribution type, that is if it's your uniform, normal, or your bimodal, this particular, let's say you have to draw a comparison between your box and violin plot, this is how it would go. For your normal distribution, your box plot would be a standard box. For your violin plot, it would be like a smooth ellipse, which is like a bell curve that you can see here. And for your uniform distribution, this again, it's just going to be a similar box, whereas your violin plot would just give you a rectangle box type thing, which will represent flatness of that particular distribution. For bimodal, it would be another standard box, whereas for your violin plot, you could probably see two bulges that are coming in the particular distribution. And the key insight why we use violin plot is basically it prevents misinterpretation of the data. It shows a complete picture. You can also see which has a higher probability, lower probability, and your median, interquartile range. Everything is present in one particular picture. Now, moving on to your filter based and wrapper based methods, all of these come under your feature selection. So the main goal is to ensure that you have optimized set of features. Let's say you have lots of features, right? It can show overfitting, it can be slow in training, and the complexity ends up being really high. And your irrelevant features also, they cause noise in prediction. You have redundant features which cause multicollinearity, and all of this arises because you have unnecessary features, too many features, repetitive features. So we need to ensure that we tackle these problems, and that comes under your feature selection. Now, the methods in which you can perform feature selection is basically filter based and your wrapper based methods. So your filter methods are basically your simplest approach. It is independent of my model that I'm going to use. The core concept is basically it is used during the pre-processing step itself, and it happens based on your statistical measures. Like you have your common techniques such as your correlation coefficient, chi-square test, mutual information, variance threshold. Characteristics involves like it's really fast, it's scalable, and it's model agnostic. But the thing is it ignores feature interactions. It does not consider model performance, and that is your biggest disadvantage. Your flow would be, let's say, like an example flow. You have data and that calculates scores. Based on that, you rank features. You're going to select your top k features based on whatever technique that you're using to filter out data. You're going to train your model according to that, and it is completely independent of your machine learning algorithm. And you again check your whether it's crossing your threshold, and then you would update your selected features. Then comes your wrapper based methods. So your core concept is basically you have different subsets that are there in your features itself, and this is based on your learning algorithm that you will be using. Common techniques is basically you're having a forward selection, backward elimination, recursive feature elimination. So your forward selection is basically you have zero features in the beginning. You start adding one feature at a time, and the one that improves the model the most will still be retained, and you'll stop when there is no more improvement happening. Backward elimination is basically you start with all the features, you remove one feature at a time, so the one that hurts the model the least, and then you stop when the removal hurts the performance. Now, your recursive feature elimination is you train your model on all the features, rank features by importance, you remove your least important features, and you repeat until your desired number of features are attained. Now, your characteristics is basically you consider your feature interactions, right? But in your filter based, you did not do that. It optimizes based on your particular model that you've chosen, but it is computationally expensive because you keep going in this particular loop where you're selecting the best subset, right? And there are risks of overfitting. There is also another thing that we do, that is your recursive feature elimination with cross validation. It's just an enhanced version of your recursive feature elimination, which prevents overfitting. Now, the key innovation in this that you have cross validation at each elimination step. So your process will look something like this. You start with all of your features. For the current feature set, you will perform like your k-fold cross validation. You will calculate your average performance. You remove least important features, and then you repeat these steps until you select feature set with your best cross validated score. And this is obviously better than your RFE because it is a little bit more robust since you're using cross validation. It can generalize to data better, and you can also prevent selecting features that only work on your training data. So now we've finished this particular aspect, we'll move to your perceptron. Now, this is just going to be a little bit kind of a building block of your deep learning, where it's just a simplest model and it's kind of like the foundation of everything. It's kind of, when you look at it itself, you can probably think about your biological neuron, where these inputs kind of act like your dendrites. The weights that are over here are like your synapses, and you have your some activation that is like your entire cell body processing that is happening, and your output is like your axon signal. So it's like a mathematical model in which you have your input set, that is your x naught, x1, x2 up until xn. What you do is, and each of these are assigned weights, like which feature do I give more importance to, and that is determined by weights. And you can have bias, but in this particular case you do not. So you perform weighted sum, that is your x naught into w naught, x1 into w1, and you perform a summation of all of this. And let's say you have a particular threshold, then you have to check whether or not it crosses that threshold. If it crosses that threshold, that particular neuron will fire and it will give, okay, you can activate this output. The limitation of this is that it can only learn linearly separable patterns. It can solve like your AND OR problems, but it cannot solve your XOR problems. So with this, the perceptron part is completed. I'll just hand it over to Kamlesh to explain the linear and the logistic regression part.
Hello guys, this is Kamlesh and I am from ADS and I am Harshini's classmate. I hope you are all preparing well for your exam. So I hope you don't have any doubts up until now. If you have any doubt, we can take it. You can put it in the chat box. Yeah. So I'll just start, and if you have any doubts, you can always drop it in the chat box. So just a minute, I'll just set it up. Okay, so as we are starting from the concepts that you have all requested, the next concept that was requested was linear regression. So let's get started with it. Yeah, so this is simple linear regression, and for this, you will be asked the mathematical construct that is given over here. So since you don't have a formal background in linear algebra, you won't be asked much about like numericals and sort of uh, very mathematical stuff. So it is just okay enough if you just like understand what is given in this PPT, the 2 3 slides. Okay, so let's go line by line. So for example, we are given a data set of n statistical units. This is, let's consider this as the given data set. This is in the form of like yi comma xi1 xi2 etc until xip. A linear regression model assumes the relationship between the dependent variable y and the vector of the regressors x is linear. So a linear regression is always between x-axis and y-axis. If you imagine it in the graphical sense, it is basically predicting the y for a given x. You will have the values for a few, like from the training set, you will have the y values for a few data points of x, and you will be asked to predict the value of y for some unknown quantity x that is not in the training set. So for predicting such combinations, we use linear regression. So this is simple linear regression. So the essence is basically plotting a straight line, uh, a, s- a straight line in the graph, xy graph. And for fitting that line, you need two things. You need the intercept, that is the bias over here, the b0, and then you need the slope. Uh, so you need the details of x and y that is given in your training data set to fit the model. By when I mean fitting the model, I mean it is just creating the graph. So if you know what your intercept is and your slope is, that means you literally know how to fit the model. That means you have already fit your model. So after you fit the model, you can just find the value of like value that you are asked by looking at the corresponding x value. Okay, so this is the mathematical formula that you need to learn. Yi is the okay, wait, I haven't introduced you to this, the nomenclature. So y is called dependent variable because it depends on x. Simple. And the x is called regressor. It's just a fancy name given to x. That's it. So the dependent variable yi is equal to b0 plus b1 x1i. These x1 xi1 xi until xip, these x values are given in the training data set that is given to you. You don't need to worry much about the specifications of how do you get the data set and how do you get the beta values. You won't need to worry about it because you just need to write the mathematical formula. You will learn all these when you complete courses in linear algebra and exploratory data analysis in the next upcoming semesters. So this is the basically this is the mathematical formula for a linear regression. This we can represent in terms of a matrix like this. Here y is equal to this matrix of all the y values. So a data set comprises of many rows and columns, right? So the rows correspond to each entry, each data value. So for y1 is dependent on many x variables. These x variables are basically features. So suppose there are five features. If there are five features, you will have five rows in this matrix. This is x1 transpose, x2 transpose, and so on. So this is basically the feature. The first feature, second feature, up so on until the nth feature. So this you'll be given a series of values. This you are representing is it as follows. I hope you understand this. And the beta values are also given. These are error terms. Error terms are just to like when we'll see it in the next upcoming slides. So we need to find the error rate and how much error is produced in the current iteration of the machine learning model. So the point of the supervised learning model is to reiterate, go on and on until you find a minimum error. So for that error, you need a metric, right? That is this error. So there are multiple ways to compute errors. The most common one is simple ordinary least squares. Okay, we'll cover those syllabus when we come there. So this is the terminology. I hope you would have gone through all these already. Anyways, I'll also just go through them again. So X may be seen as a matrix of row vectors. All these I already told you. Beta is the parameter vector known as the regression slope. So beta is basically, if you have seen, observed, beta is the slope that is present for each and every term. These beta values together create the slope of the final line. And E is the error term or sometimes noise. Okay, so let's move on to assumptions of linear regression. This is a teacher's favorite question, so you might expect this question as it is directly. You can just easily get the marks. So, okay, I'll explain each and every assumption. First one, weak exogeneity. This means that the predictor variable x can be treated as fixed values. For example, the predictor variables are assumed to be error free, that is not contaminated with measurement errors. Assume when training the model, the x values, the predictor variables itself are error. Like there is a sensor error due to which the x value, which has to be 5, is mistakenly recorded as 50. Then what will happen? The model that is trained on these predictor variables will also be faulty, right? So linear regression, while training the model, we assume that all the x values are fixed. That is, they are not error prone. They are all error free. So that is a base. So the entire linear regression is based on the x value. So this is the first feature, like the first assumption. Next assumption is linearity. Of course, linear regression itself tells that the line is going to be linear. So you cannot expect curvy lines to predict the values, right? So that is what is said here. This means that the mean of the response variable y mean is a linear combination of the parameters beta and predictor variable x. This jargon is might not be familiar to you because you haven't taken the linear algebra course, but what it says is that it basically says that y is equal to sum of products of beta and x. That is basically, here it's written, right? Beta and x. So beta 1 x1, beta 2 x2, and so on. So it is sum of products. That is what linear combination means in essence. That's it. Next assumption is homoscedasticity. As you know, this question has occurred in the previous year question papers many times, so it's very important you know the meaning of it. This means that the variance of the errors does not depend on the values of the predictor variables. Thus, the variability of responses for given fixed values of the predictors is the same regardless of how large or small the responses are. This means that basically when the as the predictor variable x increases, it means that the variance should not increase. So in the graph that we have seen for homoscedasticity and heteroscedasticity, you can spot the difference. The difference is that in heteroscedasticity graph, as we go towards the right side in the x-axis, you will see that the variance along the predictor, the line that we drawn, the data points, you can see that the data points are more scattered. That essentially means that the variance is high. That should not be a case in linear regression. That is one of the assumption. So this is what is said here. You will understand better if you try to relate the definition given here with the graph. Okay, that's what it said here. The variance does not depend on the values of the predictor variables. That's as straightforward as that. The next assumption is independence of errors. This assumes that the errors of the response variables are uncorrelated with each other. So the response variables is basically the y axis. So it means that one output y is not correlated with the other outputs y. So this is the meaning of it. Okay, so assume that you have created a linear regression model. How do you know that whether your model is good or the model that your friend created is good? For assessing this, we have something called R square score. So this is basically this tells how good your model is. It is calculated by this formula 1 minus summation y true minus y predicted. Y true is basically the y values given in your data set, or sometimes it will be given in the question itself. And y pred is the y value that your model has predicted. Yeah, so basically if you just plug in your y true values and y predicted values in this formula, you will get how, like, you will get the R square score. The best possible score is 1, and it can be negative because the model can be arbitrarily worse. So for example, uh, yeah, this number, this entire term, if it is less than 1, for example, like 0, if it is 0, it is the best possible score because this is 1 minus 0 and R square becomes 0. I mean, R square becomes 1. And it can be negative also, as it is said here. Yeah, that's it. The constant model that always predicts the expected value of y disregarding the input features would get R square of 0. Yeah, so if your y predicted and y true are already like are almost every time, if both are the same, then this value itself will come up to be 1, and that will cancel the other one and it will give us R square score is equal to 0. Yeah. So this is the next concept is confusion matrix. I hope you won't have any confusion in confusion matrix because it's as simple as this. Okay, so just remember the sequence of the cells here. So the top one is predicted and this one is actual. The rows are actual conditions and the columns are predicted. So here, if what you have predicted is positive and and the actual condition itself is positive, it means that you have predicted good, fair. This is called true positive and it is in green color because you have predicted it correctly. But in the other hand, if you predict it negative, but in actuality it is positive, it is called false negative because you have falsely predicted it to be negative. You get it? So, but it is actually positive. You have predicted it to be negative. That's called false negative. Just remember this part. The first one means the whether your prediction is correct or not. So the first word, if it is false, it means that you have predicted falsely as negative. That's what this means. And the other case where it is like you are predicting it to be positive, but it is actually negative, it is called false positive. And when it is actually negative and you also predict it to be negative, then it is called true negative and you have predicted it correctly, so it is called true. So all these will come during classification tasks. Okay, this is an example exercise given to you. I hope I don't have to cover all this. You would have done it in class. Just go through all these because similar type of question can directly be asked in your exams. Okay, the next one. Yeah, and so many people have asked this also whether this code will be asked for the exam. This code, these codes are just for your understanding. It won't be like there are very less chances that these questions could be asked as code because it is mostly testing whether you know to solve a confusion matrix, whether you can plot a matrix of your own. You won't be tested whether you can write the code for the computer to do it. Anyways, just look at this also, just in case they ask it, and for your own knowledge also. So the first four lines, and many people have asked about the code. So if you look at all the codes that you have in your syllabus, it will all contain a same pattern. First, we'll import all the necessary libraries, and then we'll like take the data as input. We'll just assign variables for the data that is given to us, and then we'll create something. In this case, we are creating a confusion matrix object. This confusion matrix is imported from sklearn metrics. Okay, so this confusion matrix function is taking actual and predicted arrays as input, but these are not just normal arrays. You have to give them np arrays. np.arrays basically creates a numpy array of the normal list that is present in Python. Why this is done is because numpy arrays are faster to process and it is it is stored in the memory in such a way that it could be used for many many libraries basically want that kind of representation in the memory. So that's why NP arrays are preferred for majority of the libraries in machine learning. And SNS is Seaborn. Seaborn is a library for plotting. So here we are creating a heat map. There is no other way, guys. The order of the parameters that all the functions take, you have to memorize it. There is no other way. But yeah, as I said, this has very less chances to be asked in the exam, so you can just chill about it. Uh, okay. This sns.heatmap, this line will create a plot object and plot dot y label is for the label for the y axis, as you can guess. And this is similarly for x label, x-axis. This is the title of the plot itself. And one point to note, this PLT is an alias for pyplot, matplotlib.pyplot. So if you don't include this line, you will have to write matplotlib.pyplot everywhere instead of PLT. So that's why this line is present. And finally plt.show. Yeah, so this will create the confusion matrix for this. Actually, this image itself is the output of this code. If you run this code, you will get this image as the output. Yes. And this is another code. We'll come to ordinal encoders. Like we will cover all the codes at the final segment. So just wait for it. I am skipping it for now. Okay, the next one is okay. So now we are entering into few statistical parameters. I hope you will already know all this. You have no other way. You have to memorize all these formulas. I can tell you like tricks how to memorize these formulas. Accuracy is basically when uh, okay, so in accuracy the numerator consists of the truly predicted values, true positive and true negative. These both are when true positive is when as you know it is actually positive and you also predict it to be positive. True negative is when it is actually negative and you also correctly predict it to be negative. So the numerator consists of TP and TN, the correctly predicted ones, and the denominator consists of all the other values. So accuracy is very easy. For this image, 5 plus 3, okay, if you see the previous example, you will have better idea. The next one, precision. Precision is basically true positive by true positive plus false positive. So the denominator, both of the denominator, like the both of the terms in the denominator consist positive values, true positive and false positive. It means how accurate your model's positive predictions are. So when you predict something to be true, how how many of the times it is actually true and how many of the times it is false, but then you tell it to be true. That is what this measures. I'll just take a quick example for this. 5 by 5 plus 1. Okay, let's go and see in this example. 5, okay, TP by TP plus FP. This is TP and which is FP. Yeah, so this is FP. So if you see, FP is when it is actually not a dog, but then you predict it to be a dog. So this means that 5 by 6 is the precision that you get, right? It means that 5 out of 6 times you are predicting it to be correct while it is actually correct. But then the other 1 by 6 times you are wrongly predicting it to be not a dog, but then it is actually a dog. So as you see, you are only considering the true positive outputs, not the negative outputs. So this is precision. I hope you understood it. The next one is recall. Recall is basically true positive by true positive plus false negative. False negative is when it is actually true, but then you tell it is negative. You have wrongly identified it as negative, but it is actually true. I mean, actually positive. So this is also coincidentally 5 by 6, I guess. TP by TP plus Fn, right? Yeah. So this is also 5 by 6. So what it means that is that 5 by 6 of the times you are predicting a dog correctly, but then the other 1 by 6, like other 1 by 6 of the times, it is actually not a dog, but then you tell it is a dog. That's what it means. Okay. So this is recall. So these are the three statistical parameters. The next one is F1 score. F1 score is basically 2 into precision into recall by precision plus recall. It's basically yeah, this is the formula for it. It's a harmonic mean of precision and recall. You can just calculate all these. Don't forget to get your calculator inside the exam hall. Okay. The next concept is ridge regression. Okay, so ridge regression is where you estimate the coefficients of multiple regression models where the independent variables are highly correlated. So there is a problem when there is high correlation between the independent variables. At that time you use ridge regression to solve that problem. This happens in multiple regression models. Multiple regression models mean there are multiple features for one value of x, like for one value of y. And in statistics, OLS, ordinary least squares, is the type of least squares method for choosing the unknown parameters in a linear regression model by principle of its least squares. Okay, so when you want to improve your model, you have to check the error rate, right? So you do it by checking the error rate using this ordinary least squares method. After each iteration of your model, your model training, you will measure the least square error, and then you try to fit in the model again. Yeah, so this is the important slide. Okay, just a second. Okay, yeah. The coefficient estimates for OLS rely on the independence of the features. As I said, if two features together contribute to the y, and two or more features for that matter, suppose two features are highly correlated. For example, if feature 1 is 2 and the feature 2 is also like the feature 1 is scaling to twice every time and the feature 2 is also scaling twice every time, it means that their coefficient of, like, the correlation coefficient is very high, right? So when that happens, the columns of the predictor matrix X, as we remember, we saw this predictor matrix X in simple linear regression. Here in linear regression we saw this. These are the features X. So these are multiple features are present. So this is the multiple regression model I was speaking about. So in this X, the in this X matrix, if both, like if two features are highly correlated, then uh, just a minute. Yeah, when features are highly correlated, the columns of the predictor matrix X have an approximately linear dependence. So it is no longer a multiple regression model, right? You can just reduce it to a linear model because the features are linearly dependent. The least squares estimate becomes highly sensitive to random errors in the target. So instead of measuring the actual required errors, the model starts becoming highly sensitive to the random errors in the target Y. So these random errors, these random errors are unpredictable, and hence you'll get a large variance and the model you train won't be a good one. So this is the problem with multiple regression with similar coefficient estimates of the predictor variables in a multiple regression. For combating this, we are using ridge regression, and this is a small code for ridge regression. This also there is very little chance of showing up in the exam, but just see it once so that you won't be surprised when it comes, if at all it comes. Till this part, all the code is the same template. First, you are importing all the necessary modules, and then you are creating a data set. In this case, you are fetching California housing data set. There are a few data sets which come inbuilt within the sklearn itself, scikit-learn. So this California housing data set is inside the sklearn.datasets. So you just fetched it and uh, assign the variables x and y for the data and target respectively, and this you are scaling it as usual. You always have to scale before you apply a model. And then this is the test train split. So the train test split is the function's name, and scaled x y are the inputs, along with test size equals to 0.3. Test size equals to 0.3 means 0.3%, as in 30% of the uh, total data will be taken as test size, test part, and the training part will be of the remaining 70%. So your model will be trained on random 70% of the data, and the other 30% will be used for the testing purposes after your model is being fit. So for the output for this is a tuple, and you can just directly uh, assign each value like this. And then this is the ridge regression, the actual part. Uh, yeah. So you don't have to care about all these alpha, toll, solver, and all. This is basically out of syllabus. You won't be asked this code. But if you are interested, you can go and search online. I think this is a link. Yeah, you can click this link and open the Geeks for Geeks website and you can learn. Yeah, that is it. This is the end of ridge regression. Okay, now let's move on to logistic regression. Okay, logistic regression is basically you apply a logistic function to the data that you have. For example, consider this data set. This data set means that this is not the actual data set. This is after you apply the logistic regression. Okay. So suppose you have, wait, this data set is not given. Okay. That's not a problem. Okay. Once you have a data set given, you can apply the data set to this function. This is called the logistic function. This is a sigmoid function. There are multiple logistic functions that are available, for example, ReLU, softmax, etc. But here we are using the sigmoid function, and if you apply sigmoid function for the z value that you are given in the data set, you will get a probability, and you can plot the following graph. So if the probability is greater than 0.5, you can label it as yes or positive. If it is less than 0.5, you can label it as negative or no, and so on. So this 0.5 is a threshold, and you can set your own threshold. Yeah, so all these are theory. You can just learn it yourself. Yeah, assumption, binary outcome. Okay, so as we said, we can only classify whether something is failure or success, or yes or no, and so on. It is the outcome variable is binary and independence of observations. So similar to the observation assumption we saw in the linear regression, this also assumes that the data, the x values of the data are independent of each other. That is, the like one observation must not influence the other observations. And the linearity of log odds. Log odds, this is the function, this is the formula of log odd. So basically, if you apply this formula to the data set that is given to you, you should find that the graph, the resulting graph should be in linear nature. To understand better, assume this graph. This is a logistic graph, right? So, okay, since you, okay, you haven't completed uh, linear algebra course. Okay, for now, it is enough to understand that this log odds should be linear in nature. That's it. The relationship between the predictor variable and the log odds of the outcome is linear. In linear regression, we saw that the relationship between predictor variable and the y is linear, right? Because it is linear regression, the relationship between x and y should be linear. And x is the predictor and y is the predicted variables. But then here, instead of the x value, we the log odds of the outcome must be linear. The outcome p of x is basically the height, the corresponding height. For example, if you take 0, if you take 0, the height is 0.5. 0.5 is the p of x in this graph. Okay. So if you apply p of x by, log of p of x by 1 minus p of x, and if you plot a graph between x and all the log odds, you should get a linear graph. That is one of the assumption. Yeah, that is what is given here. P of x is the odds of event occurrence. 1 minus p of x is the odds of not occurring. The event is not occurring. So for applying logistic regression, this should be satisfied. This is basically nothing but saying that this term and x term are linearly related. That is what this means. It is a linear combination of this x and this term, this y. This is the log odd term. If you compare it with the linear regression model, it would be similar. This was y and this was kx and the error term and bias term. K was the slope. Here instead of y, we are writing a log of p of x by 1 minus p of x. That's it. And the next assumption is absence of multicollinearity. Yeah, so the predictor variables must not be multicollinear. In linear regression, when there was multicollinearity, we saw that one way to combat that issue was ridge regression, right? So the same problem holds here also. Multicollinearity must not be there. That is our enemy. And the sample size must be large. For some reasons, logistic regression performs best when the sample size is large. Yeah, there is no strict rule for the minimum sample size, but it should be sufficiently large, the sample size. That is it. Only if you have such a large sample size, the inference that you get will be reliable. Okay, the next one is sensitivity and specificity. Yeah, sensitivity is the same as true positive rate, the one we already saw. True positive rate is basically TP by P, where P is what? TP plus FP. That's what P means. And specificity is true negative rate. Yeah. So false positive rate is FPR. We already saw it. FP by FP plus TN. F. So this is basically recall. We saw it in the previous slides, right? This is recall. And 1 minus specificity is FPR. Okay, then. Okay, yeah. I hope you know all these concepts very well. Area under ROC. This was not asked in the form that was circulated, so I am skipping this part for now. Yeah. So this PPT is over. Okay, let's have a short break of 5 minutes, after which we'll continue with the coding questions.
Okay, guys, we'll be starting with the coding session right now. First, we'll start off with a small cheat sheet that we've made for you guys so that you know which libraries to import when you're calling which function. And mostly, you won't be using all of these that you're seeing over here. It's just, okay, kind of a cheat sheet that has everything that you would have learned throughout this. Now, mostly you will need your imputation, scaling, encoding libraries, your basic libraries that are your import numpy as np, pandas as pd, matplotlib.pyplot as plt, import cborn as sns. And then your imputation library is just your sklearn.impute, through which you can input, import simple imputer and your knn imputer. And from your pre-processing library, you can import all of your scaling as well as your encoding functions that are your standard scaler, min-max, robust, your normalizers, label encoders, on-hot, and ordinal. Now we've prepared a set of questions for you guys on demand because this is completely exam focused and it's all based on what was asked in your previous year question papers, and all of them are really trivial. You don't need that to spend that much time on them, but it does require a level of understanding of the underlying, working of the functions and everything. So we've compiled this notebook so that you can have an entire set of previous year questions code that were asked the past 2 years in one place. So we'll start off with your ordinal encoding question, where you have to write a Python code with an expect, and you have to expect the output also on this particular data that is provided to us. There is your Batman 1, Superman 3, Flash 2. Now, for better visualization, your Batman, Superman, Flash, they're all in one column. 1, 3, 2, they're also in one column. But when we're writing it in code, we always write it in this manner. So we might presume it as a row, but they are not. Your Batman, Superman, Flash, they all fall under one column. One, three, two, they're another column. And also remember, this is a really common mistake that is made. Anytime you are performing imputation, scaling, or encoding, ensure that you do it column wise, not row wise. Uh, a small mistake could cost you a lump sum mark to be lost. So just keep that in mind. Now I'll teach you a small short trick, and also Kamlesh also specified this. It is something that is like a blueprint, a skeleton to be followed for all the questions that are to come. Where first thing, just import the library that you're using. Like without this line, you will not get full marks. Since we're using an encoding technique, we're gonna take up your pre-processing library and you're gonna import your ordinal encoder. From this, we first write our data. Now you write over here, the data is presented as it is. But when we're writing our data, always ensure that your rows are written like this. Do not write them in terms of your columns. You need to write them in terms of your rows. Now over here you enclose it in the bracket. You do not need to convert it to a NumPy array because you're writing it like this. So this saves you a little bit of code that you are using, or converting it to your array space. After that, you're going to declare a variable which will hold your ordinal encoder function, after which you're going to have your output data that is over here, that will ensure that this particular encoding technique has been fit. That is, it learns from this particular data and then transforms, it applies what it learns to that data itself, and then you're printing the output. Now, this 5 lines is standard. The only thing that changes is what you're importing here and from which library you're importing it, and the data that you're using. Over here, the whatever library you have imported, that will change, and your output will print accordingly. This is a standard template. Follow it for everything that is upcoming. Now, since it's Batman, Superman, Flash, again, like I told, column wise, just continue with it. Batman will have zero value because it is, and you have to do it according to ASCII. So B will come before F and then S. So it has been written according to 0 to 1, and your 1, 3, 2 are also treated as your categorical values for ordinal encoding. Therefore, that also will be encoded into your 0, your 1, and then your 2. So your code and your output should be written like this. Now, second question is you have to write it for your male from US uses Safari, female from Europe uses Firefox. Again, male, female will fall under one column. From US, from Europe, another column. Uses Safari, uses Firefox, another column. So we have three columns, right? First thing, we are importing our library, done. Data, we're writing it in terms of your ensuring that you're putting your proper brackets where each row is specified like this, and then you're representing like that. Then you have your encoder that is called, and you're performing fit transform and printing the output. Your output should be, now again think about it. As according to ASCII, you'll take female as 0, male as 1 from Europe and from US, right? Again, till this particular space, it's the same. So your differentiating factor is E, and over here it is U. So again, this gets 0, this gets 1. So uses Firefox. Over here, the differentiating factor is F and S. Therefore, this gets 0, this gets 1. After which you'll get your output like this, specified within the same brackets. Next, we'll use ordinal encoding in this particular matrix as well, where it's male 1, female 3, female 2. Where male, female, female is a column, 1, 3, 2 is a column. Now you have to provide the code. Again, same skeleton. You're importing library, specifying data, taking the function, fitting and transforming the data, and printing the output. Now, wait, let's guess the output. Now, there's male, female, female. Again, F has a lower value, so it will take up 0, and male has 1 value, so it will take up 1. I mean, it has a greater value, so it will take up 1. Therefore, it will be what? 1, 0, 0. And over here, I mean, 1, I mean, what? It'll be 1, 0, 0, correct only. So over here you have 1, you have 3 and 2 present in a particular column. Again, it will treat it as categorical values. Therefore, 1 will be given 0, 3 will be given 2, 2 will be given 1. So your output should be 1, 0, 0 and 0, 1, 2. Next is your one hot encoding. Now, in this particular one hot encoder, we need to ensure that whatever data we're writing, it needs to be in a column format. Over here, we skip that particular format because we wrote it in particular brackets perfectly so that it forms your column format. But over here, let's say you want to do another way. There's another method of doing it where you use NumPy array. You'll have to reshape it so that it becomes a column so that one hot encoder can work with it well. Therefore, we use np.array and then you specify the data as it is and then you reshape it so that it transforms into a column. Again, this step can be skipped, but in case you want to, represent it in terms of a NumPy array, this is something that you can do. Let's say you don't want to complicate it by calling more libraries, then you can follow this particular method where you have a square bracket here, apple is in one bracket, banana is in one bracket, and you just encase it accordingly. Now here you'll have to ensure that you declare sparse output is equal to false. This is really important to printing your output. Now let's say I'm removing this. You can see the output change. You just get compressed sparse row matrix with your float type. But since you want a particular perfect matrix and you need to be able to ensure that you're getting what you wanted out of it, so we'll put sparse output is equal to false. Now you'll get the particular encoded values. Now since you have apple, banana, cherry, and apple, your unique values are, I mean, unique values are like your apple, banana, and cherry. So each of them will get a column according to your ASCII value itself. So apple will be your first column, banana will be your second column, cherry will be your third column. And based on its occurrence, it will get 1 if it is present and 0 if it is absent. So for apple, you'll have 1 0 0. For banana, you'll have 0 1 0. For cherry, you'll have 0 0 1. Apple, again, you'll have 1 0 0. So that is with one hot encoding. Now Kamlesh will take up your scaling techniques.
Okay, so let's move on to scaling techniques. The first one is min max scaler. So we are given this so we are given this data set -1 to 0 point, -0.56 0 10 118. So we have two columns and four rows. The first column is -1, -0.5 0 and 1. The second column is 2 6 10 and 18. So I hope you got it. We have the four rows and two columns. As you can see, this is not in proper scale because this is in this is going in -1 0 -0.51. As you can see, it ranges from 0 -1 to 1. But then the other feature, the second column, is ranging from 2 till 18. So both of these are in different scales. For bringing them to the same uniform scale, we use the min-max scaler. So data equals to, okay, the first line is, as Harshini said, we are basically importing min-max scaler from the sklearn.preprocessing library as usual, and then assigning the data to a variable, and then scaler. We create a scalar object. Here we are using min-max scaler, so the min-max scaler we imported from the sklearn pre-processing library, right? So we are creating a min-max scaler object and assigning it to a scalar variable name scaler. You can name the variable anything you want. The next line is output equals to scalar dot fit transform of data. Here the scalar, the previous line we created the scalar object. So in this scalar object, we are applying the fit transform method. Fit transform method is used to fit and transform using the same data points. If you want to fit the scalar using a different data point and transform it to a different data set itself, you have to fit the data in one line and then transform the data in another line. But then here, since we are fitting and transforming for the same data points, we are using the function fit transform. It just makes our lives easier. So fit transform of data, we are storing the output in the output variable and then we are just printing the output. So as you can see, the output that has been produced now is scaled using the min-max scaling algorithm. So as you can see, both the columns are in the same scale. The scale here is 0 to 1. For min-max, it is always 0 to 1. Yeah, so this is the output. Okay, yeah, we can move to the next one. Next question. Harshini? Okay, the next question. Here we are using max upscaler. So, okay, we are given a data set as usual. First line, we are importing the marks of scalar. Second line, we are setting the data and assigning it to a variable. So you can write it like this: 1 minus 1, 2. You can just basically copy the question. So here, if you see, this is a 3 cross 3 matrix. The next line is scalar equals to max of scalar, as we did it in the previous question. Previous question we use min max scalar, now it is max of scalar. That's the difference. That's the only difference till now. And then output equals to scalar dot fit transform of x. This is the literally the ditto same line as we wrote in the previous question, and printing the output. So this output will give the max of scaled version of the data set. And here, as you can see, the range of the output is from -1 till 1. Okay, next question. Okay, this is standard scalar question. First line, we are importing the data. We are importing the module, then setting the data to a variable scalar, creating the scalar object. Here, standard scalar output equals to scalar dot fit transform, the same line as we wrote before, and printing the output. All these steps are exactly the same except the two lines. Here, standard scalar, here also it's standard scalar. That's the only difference we have seen so far. So the standard scaled output is this for this corresponding data set. Next, we move on to imputation techniques. Okay, so in imputation, in the previous questions, in the scaling questions, we use the libraries from the sklearn dot pre-processing. But then here we are importing libraries from sklearn dot impute, because it is imputation, simple imputer. So the simple imputer library is inside sklearn dot impute. Okay, so you might be wondering why we are importing NP here, but we didn't import NP in the previous questions. It is because here we are representing the unknown variables using nan. This nan is inside NP. So that's why we need NP. We need to import NP. NP.nan. NP.nan means something that is not found, not a number. That's the abbreviation of nan. So the data is as follows. Just take it in, from the question. And imputer, you can name this variable with anything you might like. Simple imputer with strategy equals to mean. In the previous questions, when we were scaling, we just wrote max of scalar, min max scalar, like that, and then we just open and close the brackets without any parameters. But then simple imputer takes strategy as a parameter. You have to mention it. So here we are taking the strategy as mean. You can take the strategy as mode, median, anything. So it'll train the model using the mean. So it'll fill the missing values using the mean of those particular columns. So output equals to the imp variable dot fit transform of data. Data is the variable here. If you print the output, this is the corresponding output. You might be wondering why the both rows are literally the same rows. It's because here in the first column np.nan is there and 4 is there. So while taking the mean, there is only one object, right? So you just do 4 by 1. So that's why you impute the np.nan by 4 itself. Similarly, for 2, this np.nan will become 2, and for this np.nan will become 3. Since there are only one point other than the np.nan in that entire column, you are getting the np.nan also to be the same data point as the other, as the number one. The next question. Okay, in this question also we are basically imputing using the simple imputer. Nothing is different. The same steps: first import, and then the data, and then simple imputer object, and then fit transform the simple imputer and print the output. All the code remains exactly the same, only the data changes. And one point to note, when it is asked in your exam, even if the exam paper, if the question asks you to only write the code, it is better you write the expected output also, even if it is not mentioned in the question. It just takes extra 2 minutes, right? It's not bad to write the output. You can create a better impression in the teacher's mind if you do that. Next question. Okay, the next question, this is also the same similar simple imputer question, but then as I said before, here we are fitting the simple imputer using a different data set, and then transforming the simple imputer using another data set. So in the previous questions we did imputer dot fit transform, but then here we are doing imputer dot fit, and inside fit you give the fit data. This is given in the question. It is given here. See, fit the simple imputer to this data and transform this data. That is what you are doing here. Fit data, transform data, fitting for the fit data, and then imputer dot transform of transform data. Transform data you are transforming. So what happens internally is that it takes the values from the fit data, and then takes the corresponding mean value, and then replaces the np.nan in the transform data set. So here let's work out for one column. This column, it is 1 3 10. So the mean is 14 by 10, which is 4.8. This 4.8 will be replaced as the np.nan in the first column. So in the first column, this np.nan got replaced by 4.8, as you can see in the sample output, in this output. Yeah, so similarly for the second column, this is 1.2 np.nan, yeah, 1.2 and 5. So that is 6.2. 6.2 by 2 is 3.1. So this 3.1 will be used to replace the np.nan in the second column. Here there are two np.nan, and both the np.nan are getting replaced by the same 3.1, as you can see. Yeah, so similarly, this is how it works. Let's move to the next question. Okay, in this question we are using Canon imputer. Okay. In the previous question we did like we imported simple imputer. Here we are importing the Canon imputer. Not much of a difference. Data, and then imp equals to Canon imputer, n neighbors equals to 2. The previous questions we did simple imputer strategy equals to mean. Here the parameter that Canon imputer takes is n underscore neighbors. We are setting it to 2. As you might be familiar with how Canon imputers work, so here we are taking the n values as 2. So it measures the nearest neighbors, two nearest neighbors for each and every nan value, and then replace the nan value by the according to their nearest two neighbors. Output equals to imp dot fit transform of data, print output. All the other lines are exactly the same. So if you work out this question, np.nan is in the first column, right? So in this column, only the third row contains np.nan. So if you calculate the distance of this coordinate with all the three coordinates, you will get the nearest two coordinates. So using the two coordinates that you get, the two nearest neighbors, you get the you take the corresponding x, I mean you take the corresponding the first column of the two neighbors. uh just a minute. I suppose here I think the two nearest neighbors to this third row are the second and third. And just a minute, I'll just confirm. Yeah. So for this row, the third row, np nan comma 6 comma 5. For this row, if you calculate the distance using the RMS, you'll get 343 and 887. These rows are the two nearest neighbors to this point. So taking these two rows, take the first column 3 and 8. Take the mean of 3 and 8, you get 5.5. So you impute this np.nan using the 5.5 that you get. This similarly you can solve for the other np.nan. Next question. Okay, this question is similar to the last question. Not much of a difference. Only the data is different. All the others are literally the same. Wait, I think it is the same question as the previous one. Okay, never mind. Let's go to the next question. Next question. Okay, okay, this is interesting. This might be new to you, but yeah, when it came in our midsem paper, it was new for us also. We were also as shocked as you. Just learn this also. So we are given a URL, and then we are told to read the CSV file given in that URL, and then write the code to print the statistical details, 25th percentile, 50th percentile, 75th percentile, etc. of the data set. So when I saw this question in my midsem paper, I was shocked. I didn't know what to do because we have never learned this function df.describe in our class. Maybe I was not attentive enough. So what I did was but fortunately I knew this line pd.read_csv of URL. What this basically does is it takes in a URL and it takes in a URL and creates a data frame. Yeah, creates a data frame. This is powered by pandas library. In NP, in NumPy, we saw that everything were arrays, right? NumPy arrays. But in pandas, everything is a data frame. It's just the jargon, nothing else. Data frame is nothing but a matrix. That's it. So pd.read_csv of URL takes in a URL as an input and then creates a data frame of it. And after creating this data frame, you can print the df normally to just see all the data that is present. And there is this magic function df.describe. If you print this df.describe, you will get all the statistical details about it as a neat tabular column for each feature. In this data set, there are four features: sepal length, sepal width, petal length, and petal width. For all these features, it will give all the data, all the statistical data. How many are there? Count, the mean, standard deviation, minimum value, 25th percentile, 50th percentile, 75th percentile, and maximum value. Everything it will give. So yeah, this is the simple single line output code that is expected. But then, since I did not know what to write for this, I tried making up my own functions, and I just wrote the code for finding the 25th percentile, 50th percentile, everything on my own. So that is not required. So yeah, this is the one single line that you have to remember just in case it appears. Even if something that you have never learnt in your code appears in your exam, just don't worry about it. Write whatever you know. Whatever feels right must be right. So don't lose your hope. That is all from me. Okay. Let's take a quick break for 5 minutes.
Okay, now we'll be starting off with the previous year, question solving, where this is going to be like a reference guide because we got a small feedback saying that it would be better if it is known how to frame questions properly and also ensure that it's a really, you can get good scores also, and where to use which diagrams, that also was asked. So, based on that, we have taken up two end semester papers and we will be going through each question and specifying what points to include, how to present the answer, and what diagrams to include where. So, just before starting, all the information, regardless of the question, is already present in the PPTs that were shared with you by your faculty. There's no chance that anything outside that PPT is going to be asked. All the diagrams for that particular topic, just ensure that you know it well and through. And whenever any, just remember everything by subheadings. As per your subheadings, just register in your mind that these diagrams come under these subheadings. Now, regardless of whether it is asked in the question or not, it is probably expected that if a particular topic is asked and if that particular topic had a diagram in the PPT that was shared with you, then it is very much expected that you draw the diagram also. So, with that said, we'll start off with solving the end semester examination paper of your 2024 to 25 odd semester. So, first one, it is write your Tom Michel's definition of machine learning and what are the issues of supervised learning. It was a 3 plus 3 mark question. So, just for writing your definition of machine learning that was specific to what Tom Michel had said, you would gain 3 marks. And to write that, you just need to mention there is a computer program which learns from your experience E with respect to your tasks T, given that it has a performance measure P. So, if its performance at T as measured by your P improves with E. So, that was like your definition for machine learning. It is there in one of your slides, and it's kind of little bit hard to see. So, it's something that you can miss. Ensure that you learn this definition because this appeared in our batch NSEM also and the previous batch NSEM also. So, just ensure that you don't take risks. Next, for your issues of supervised learning, there are 4 points that should be present. That is your bias variance trade off. You need to mention what is your bias error, your underfitting, and your variance error, your overfitting, and that particular sweet spot. If possible, because this is just a 3 marker, there are chances that diagram is not expected, but to ensure that you don't take any risks, draw the graph for your bias variance trade-off for this particular question. Next is your function complexity versus data. Ensure that you mention any true function that is too simple. Your learning function is too simple, then it becomes an inflexible algorithm and it will only work for your small data. But if you have a complex learning function, then it is a flexible algorithm that will work on your large data. And you need to compare and contrast how it varies according to data and your learned and your true function. So ensure that these three key terms are present. Next is dimensionality. Any data set which has a lot of features or which has high dimensions could lead to high variance and confusion, and it depends on what model you have selected to represent that particular data set or get a particular output for that particular data set. So you need to ensure that you do not cause high dimensionality. Now, one of your solutions could include feature selection so that you can reduce the number of features, thereby reducing the number of the dimensions that are present in the data. Next is noise in the output. Ensure that you note down that sensor errors, your anything that was recorded by humans could also become an error, could take it down in a wrong format. So all of these contribute to incorrect values. which will not fit according to what our model wants. And it could also, if you eradicate this particular noise that are there in your data set, then you can ensure that your model does not overfit. And you can also ensure that you don't have outliers present in the data randomly. Next, so far we've covered 6 marks. Next question was, what are the steps for supervised learning, which is a solid 4 marks. So there are 5 steps, and under each step, there is a lot of content that is provided in the slide. Just condense it and write it in your own words, that's also fine. But these 5 headings should be present. So you have to first determine the type of training examples, that is, what do you want to work with? Just make up your mind about it, after which you will gather that particular training set that is there, take the data set, and after which you're going to, whatever input feature representation that you have with respect to your learned function, you just need to ensure that, is it accurate, is it not accurate, is it providing what I wanted to provide. After which, okay, the stage has passed, then I will determine the structure of my learned function, and whatever algorithm that I'm going to use, let it be logistic regression, your SVMs, whatever will work with respect to your supervised learning algorithms. Accordingly, you will ensure that you have a learned function and a corresponding learning algorithm. After which, let's say you've determined that they are compatible, you will complete the design, and then you will evaluate the overall accuracy of your function. Is it performing well? And that you will conclude supervised learning there. But if it has not, then you will redo all the steps until you get a desired accuracy. So that is with the steps of supervised learning. Next is, explain with the graph the concept of bias variance trade off. This is a 5 marker. You need to ensure that you specify what is a bias. That is error from wrong assumptions, which can cause underfitting. Now, this is just key points. Please keep in mind that you need to ensure that the message is conveyed without losing information in your answer script. Now, when they're asking for bias variance trade off, it is essential that you say what is bias, what is variance, and what causes underfitting, what causes overfitting. Draw these 2 graphs that are present in your slide. So over here we have bias from wrong assumptions, underfitting, error from sensitivity to your training data that causes your overfitting, your total error being bias square plus variance plus irreducible error, under which you will draw a graph. Now, after drawing the graph, also ensure that you mention what you have included in the graph as well. Now, in this, you have your x-axis, your y-axis, representing your model complexity and error, and that particular region for your least value of total error should also be mentioned. And the variance curve, the bias and bias squared curve, and this is basically your underfitting zone, overfitting zone, and you need to ensure that your generalized test error is also mentioned. So your optimal point is where you get your minimum total error, that is over here. So mention all of these points and you have scored 5 marks solid. Next, the linear regression question. So the question is as follows: what are the significance of your different terms in linear regression equation? That is, y is equal to x beta plus e. Explain the corresponding matrices to. What is heteroscedasticity? I think if you guys paid attention to when Kamlesh was taking up linear regression, he also mentioned that it's something that comes very frequently. That is your homoscedasticity and heteroscedasticity. There's also a graph for heteroscedasticity, so ensure that you draw it. Another thing is, with respect to the linear regression equation, this is that equation. You just need to say what each of them does first. That is, your y is your dependent variable vector, x is your independent variable, this is your matrix size, and then beta is your coefficient vector, e is your error. How do you represent it in matrix form? Since the formatting did not support me over here, I haven't included it, but in that slide, they have shown how it is represented in the particular matrix itself. plus I think even Kamlesh covered up how to write it in a matrix. Include that, and also include what x11, x12 up until that entire thing as x is equal to that particular set. So just ensure that you have all of those details written in the answer script. And then you have your heteroscedasticity. It's just non-constant variance of errors across observation, which will violate your homoscedasticity assumption. And there's a graph. I think Kamlesh will cover that graph in the next paper, but just ensure that you know that there's a graph for homoscedasticity and heteroscedasticity. I think that showed up in our NSEM paper. Knowing it could, score you some marks. Next. Define the R square value or your coefficient of determination. Draw the perfect classifier point in ROC curve. Now, what have they asked? You have to first define what is your R square value, and according to that, like as it is in the slide, just mention the definition, and after which you're going to mention that particular equation that is present over here, where you have your y predicted, y total, that square divided by your total, and then you'll have to do it 1 minus, obviously. After which you'll just mention what each variable represents. I think again it is better explained in the slide, write it as it is. After which you have your graph that is there for your perfect ROC curve classifier. Over here, just ensure you have your ROC curve that is present, in which you have your random classifier that is going to be your base model. Anything that falls below this classifier will be a really bad model. Anything that falls above is a good, and if it's something reaching towards this particular point, then it's a perfect classifier. So just mention all of these points and ensure that you've written this 0, comma 1 is your perfect classifier point in your ROC, and write it in terms of true positive rate and false positive rate, which basically means 100% sensitivity, 100% specificity. Next thing is your logistic regression assumptions, which is basically what are your assumptions of logistic regression, which has come for a lump sum mark of six marks. So any assumptions that are taking place in terms of your logistic or your linear regression are really highly likely to appear in your NSEM paper. So please pay good attention to them and ensure that you are writing down the headings properly as provided in the slide, because what is provided to you is what is expected. So for logistic regression, you just need to ensure that you have your binary outcome. That is, it should be either zeros or ones, and your dependent variable is in categorical format. Independence is like your observation need to be independent of each other, provided there's no multicollinearity present. So none of your independent variables should be correlated with each other in a really positive manner. So it should not have that. Next is linearity. It should have a linear relationship with your independent and your logic functions. And again, Kamlesh explained this really well. So just ensure that you write that formula in which it shows your logic and your independent variables are in a linear combination with each other. Next is your large sample size. Again, your logistic regression works really well with large sample size. It's a large data set because it deals with your sigmoid function. So these 5 marks will score you your these 5 points will score you your 6 marks. Next thing is, let's say they've given you an ROC curve where you have the random class, you have 3 curves where your curve 1 is above your random classifier, curve 2 is your random classifier, curve 3 is my, like it's towards the bottom end of your random classifier. Now they've asked which classifier does the best performance, and we need to explain the reason. And your x and y axes are like your true positive and your false positive rate. When you're writing this question, first draw the graph that is given. Next, draw like your ROC graph that is like over here, and mention that anything that goes towards your perfect classifier and away from my random classifier is something that we consider as a good performance. And anything that falls below or deviating away from your perfect classifier, it is a worse, or like the model gets progressively worse. So you need to mention that that curve which has your maximum area under the curve, that will be given more importance in terms of, I mean, it has a better performance. So you'll just have to write that down, that the area under the curve is maximum. Also, with respect to your comparison to this particular graph, you can discriminate the fact that your curve 1 will belong to your good classifier, curve 2 is your random, curve 3 is a bad classifier. So your best performance is provided by curve 1. Next, the disadvantages of decision tree classifiers or learners, and what does the maximum depth of a tree signify? And the total marks for this question is 4 plus 3, that is 7 marks. So from your decision tree, you've gotten a 7-mark question that's come up. Basically, if you remember, there's that one slide which says card disadvantages. That entire slide, if you write down, you're going to get 4 marks as it is. Now, over here, you can see that first you need to mention your decision tree learners can create overly complex trees which do not generalize at all, and it can cause overfitting. That is one point. How do we curb this? Now that you use pruning, where you set like a minimum number of samples for your maximum depth of the tree. Next thing is your decision trees can be unstable. So any small variations in the data will give me a different tree altogether. So something, let's say I'm running it once, the second time I run it, I could get a different decision tree altogether. Now I can prevent this by using something called an ensemble. So let's say, or you, for example, I'm not sure how many of you would have seen it in lab. Sometimes you mention something called random state is equal to 42. This ensures that no matter which system you run it in, you'll always get the same output that you're getting right now at this particular iteration. So something similar to that is what you're going to say using an ensemble. Next thing is predictions of decision tree are neither smooth or continuous, because if you think about it, they keep branching, right? Which is very similar to how your, let's say, when you learned calculus, you had these piecewise constants that would fall under particular intervals only. So if you think about it, it's not something that is smooth. Like for example, your violin plot, when you saw that distribution, it was smooth. It won't be like that, but it will not be like, discrete also, where at this particular interval I'll get only this value. Whereas it changes, your value changes according to which interval that you're currently in. So it's kind of resembling your piecewise constant. Therefore, they're not really good at extrapolation. Next is your practical decision tree algorithms are all heuristics. That means they don't work with your actual values that are present in data, and they're also mostly like your greedy algorithm. They work with heuristics and you're greedy. When your optimal decisions are locally optimal are mostly taken up, sometimes they do not guarantee global optimal solutions. So this is one of the disadvantages. Now, how do we mitigate it? That is also you can train multiple trees in an ensemble learner where your features and samples are randomly sampled with your replacements. Also, your decision trees can create biased trees if some classes dominate. So it is therefore like you have to ensure that your data set is balanced. Your data set should, let's say, I have a data set in which I have two categories, where one category is filling up 80% of my data set. Like all the values are going to give, are like supporting that 80%, right? Now, let's say I'm training like a classifier which will learn based on this data set. Now, my training set is going to consider like have most of my the majority of it is going to be that 80%. So even if I guess every single value that I'm giving from my test data as that 80% category, then my if my accuracy ends up becoming 99, that shows that I have a bias that has been created in my result. Therefore, we need to ensure when we're training it, we have that 50-50 split. That is, your classes are equally represented. Now, this issue comes up with decision trees. Next is maximum depth. They've asked for like what exactly it is. That is basically just your maximum levels from your root node to your leaf node. And this basically controls your overall complexity and overfitting. And I think we would have mentioned in the first point itself, where we say you can use pruning to control your maximum depth. Next question is we have to write a Python code and your expected output for while applying ordinal encoder. And I think you guys can recognize this. We did this in our previous year question paper. First, write down what exactly your ordinal encoder does, after which, write down the code that we have discussed in our coding segment also. After which, write down the output that is corresponding to the code. In this, we have, like I said again, do it column wise, not row wise, because it's a really frequently made error where you end up applying the logic in a row wise, not column wise. This is especially to be taken care of when you're doing scaling or your imputation. When it comes to your ordinal encoder, again, if you have categorical values like this, ensure you're doing it according to your ASCII. In this, Batman has the least value, followed by Flash, followed by Superman. So your output will be 0 to 1 for that particular column. Next is 1, 3, and 2. Again, since you're applying ordinal encoder, even though they are numerical values, they will be treated as your categorical values and they'll be taken up as 0, 2, and 1 respectively. Again, just to reiterate for those who are not there in your coding segment, anytime you're writing code for your scaling, imputation, encoding, just ensure that these 5 lines are kind of like your holy gospel, where you have first importing the particular library, then you have your data taken up, after which you have your encoder value that is, your encoder function, after which you'll fit transform and print your resultant data. Next is now that that question is done. Okay, this was a 5 marker where you get 2 marks for writing the code and 3 marks for the output. So knowing how to get the output is also really important. Next, what are the differences between recursive feature elimination and your recursive feature elimination cross validation? Now, first things first, just write it down in such a way that the differences are pretty visible. Underline any point that makes the key change between them. First, write down what exactly recursive feature elimination does. So, you iteratively remove your least important features until and you use a single train test split. It is faster, but it's like less robust, and you'll stop when there is like no improvement in the model. Whereas your cross validation, it'll ensure that you're doing it across multiple folds of train test splits, and it's more robust but computationally expensive. It is also ensures that you have a better generalization across your data. And there is another cross validation diagram that is used when they show how for each iteration the train test split is changing. Ensure that that diagram is also included. Next question. So that previous question was a 4 marker. I think if you had written 2 points for each RFE and RFE CV, you would have scored that whole 4 marks. Next thing is, what are the advantages and the disadvantages of ridge regression? What is the difference between ridge and lasso? Again, this was covered by Kamlesh, where your advantages and disadvantages were pretty clearly specified. So your advantages was that it handles multicollinearity, and this comes up because why your logistic regression does not work well with your multicollinear data. That's why we use rich regression in the first place. And this also it reduces overfitting using something called an L2 penalty. Ensure that you know when it comes to L2 penalty, it is associated with ridge regression. It also eliminates features. That is, your coefficients that you're using, it will shrink them. But what exactly is your disadvantage? It does not perform feature selection. So all the features are ultimately, retained. And that, that basically means that we're using something that we're not technically using. I hope that made sense because it was a little confusing in the first time that we were learning it. But you have all that features which do not really provide importance, still occupying that space in your computer. So that is another disadvantage. And it also requires the tuning of that lambda parameter to get a better value. So that is another disadvantage. Your difference between ridge and lasso. Okay, over here, like I said, your ridge is your L2 penalty and your lasso is your L1 penalty. And the main difference between lasso and ridge is that it can perform that feature elimination that ridge does not perform. So whatever features that I feel like is or that particular model that we're using feels like is not important, it will directly just equate it to zero, so that whole feature is just not considered at all. So this indirectly performs feature selection. Next is something that we have not done, where it was present in the paper. This is basically time series, which you will learn in exploratory data analysis. So, but since it was present, I've written the answers for it, but it is not there in your syllabus. So, next question is you have to write the Python code to apply your one hot and your ordinal encoder on this particular values. That is your data being apple, banana, cherry, apple. And we have done this question in the code segment. Again, the difference is that you can see how it is represented differently when it comes to your one hot encoding and your ordinal encoding. When we did one hot encoding, we took apple, banana, cherry as my unique values that are present in my data set and assigned a column for each of them and provided one in the case that it was present in that row, and zero for all the others, and zero if it was not present. Whereas your ordinal encoder, it directly just takes it up in the sense that you have your unique data that is there: apple, banana, cherry. Your apple is assigned zero, banana is one, cherry is two, and it is given the output accordingly. Next. So this is basically explain with a diagram the concept of k-fold cross-validation. What are the differences between your forward selection and backward elimination? This is a 6 marker. First things first, draw the diagram of your k-fold cross-validation where it shows the train test split moving with each iteration. Second thing, mention what it is, the definition of k-fold cross-validation. Then you mention the advantages that are present well because you're doing this. And this is the process of k-fold cross-validation that happens. Your diagram should include the k boxes rotating, which is the validation set. Next is what are the differences between forward selection and backward elimination? You can just state the definition for each of them because that itself is the difference. Because forward, you start with nothing and you add one best feature at a time and you stop exactly where there is no improvement in the model itself. Next, you will also say that backward, where you start with all the features and you remove the worst ones one at a time. And also mention from which feature selection method they are coming from. Next is your simple imputer code. Yeah. So you have to write the Python code to apply simple imputer on the given data set. This data was given as it is. And you have to write the expected output. This is another 6 marker. For this, first things first, right? They have not mentioned, like, okay, think about how they have not given what strategy to use. And we all know that simple imputer has mean, median, most frequent, and constant. But default mode is mean. So since they have not provided, you can work with any of the four. But being on the safer side, I think it's better you go for mean. And another thing over here, again, since we're representing 3, 2, 5, 4, and then not a number, 7 like this, keep in mind that this is column 1, this is column 2, this is column 3. That is how you need to write it as a matrix. So your first column will include 3, it will include 4, it will include 10, it will include 9. See how there is no missing values in this column. Therefore, we do not need to perform imputation here. Next, there is 2, and then there is not a number, not a number, not a number. Therefore, we can directly, okay, by intuition we can write 2, but it is best that you write the steps that are involved to calculate that value also. So it will be 2 by 1. Again, you'll substitute everything with 2. Next is 5, 7, not a number, and 9. So again, the mean of these three values will be filled in that particular empty space. And I think the code should be clear by now. It's the same thing, same skeleton. You import the library. Since we're using NumPy, so because we have to represent that there is no value in that place, instead of writing null, we just use np.nan. After which you write the imputer with the strategy mean. Result, you will fit and transform with that particular data and you'll print the result. So that is with that question. Next thing is you have to write the Python code to apply min-max scalar on the given data set and write the expected output. And this question was asked for 7 marks. First things first, write what a min-max scalar does, the range of that particular scaling technique. After which, write the formula in which each of your values will be taken up like this, where is x minus x minimum by x maximum minus x minimum. Again, please ensure that you do it with respect to your column, not rows. So first we'll write the code down where you're importing the library, representing the data, assigning the scalar, you're fitting and transforming that data and printing that resultant matrix. So in this case, you have -1, minus 0.5, 0, and 1 in one column. And this is, you need to ensure that it is scaled. If you notice over here, your minimum value is -1, your maximum value is 1. So for each of your value in that particular column, so for -1 will be transformed into -1. Oh, just a second. Yeah. So your -1 will be transformed into -1 minus of -1 divided by 1 minus minus of -1. So which ultimately leads to 0. After which you'll do the same thing for each of the values in that column and represent it as another column itself. And notice how your minimum value becomes 0 and your maximum value becomes 1. So this shows how min-max scalar is able to bring your particular data to the range of 0 to 1. Again, in this particular column, it is 2, 6, 10, 18. Your minimum being 2, your maximum being 18. So your 2 gets transformed into 2 minus 2 by 18 minus 2, which is 0, because your above value itself equates to 0. After which, okay, let's say I'm doing another example for 6. So it is 6 minus 2, that's 4, divided by my 18 minus 2. So that is basically 6 minus 16, which will give me 0.25. So 4 divided by 16. Yeah, so that will give me 0.25. And accordingly, I'll fill the values for the rest of the column values. And there you get the output. So just for getting your code correct, you will get four. You will be awarded with 4 marks, and if you get the output correct, you are getting 3 marks. So if you write all of this properly, you're getting 7 marks in total. Next question. You have to define sensitivity, specificity. What are the assumptions of logistic regression? Now, when we're defining sensitivity, specificity, do it with respect to your true positive rate and your true negative rate. Also, ensure that you have that diagram that is like your circle. Like, for example, if you remember, there was a circle that is carved out and it shows which is true positive, which is false positive, and which is your true negative and I think, yeah, okay, that false negative. Yeah. So all of these should be present in that diagram. That should be present for this question. And another thing is the definition, your particular formula used should also be written. After which, I think there was it's a recurring question where your logistic assumptions are asked again. So, like, and this logistic regression assumption itself is 4 marks. This whole question mark distribution is 2 plus 4, where you get 4 marks for logistic assumption. If you've noticed, let's see the previous question where they asked what are the assumptions of logistic regression, that was 6 marks. And in this question, they've asked it again for 4 marks. So just by knowing that 5 points, you're gaining 10 marks solid. So do not take risks. Learn the regression techniques, their assumptions that are involved with respect to linear and logistic. They are highly likely to occur in your end semester exams. So writing that again, you will get 4 marks. The last question is basically differentiating between your KDE plot and violin plot for a total of 4 marks. Now your KDE plot, draw this particular diagram where you can see that it is almost like a histogram function being represented as a smooth, continuous probability density curve. So you just need to ensure that you write the full form of KDE, what it shows, how many variables are used for visualization, that is a single variable visualization, and whether it shows your distribution shape, and if it's a smooth continuous curve or not. So mentioning these points and drawing this diagram will fetch you the marks. After which you have your violin plot. Over here you'll show how it combines box plot plus your kernel density function, and that is your violin plot. You'll have to also say that it shows distribution on both sides. So it's kind of like a mirror effect. If this is the distribution, it will also show it in this direction, also in the mirrored direction. So that's the difference between KDE and violin. In violin, you can also see your median, quartiles, and how the density varies, which will also help us, identify higher probability regions present in the distribution. So that is another thing, and it's also better for comparing multiple groups. So if you write all of these points, you're gaining a solid 4 marks in this particular session. So that is one whole end semester paper solved. And now I hope you guys understood how to write everything properly and how to structure your answer, which diagram to use where. Now I'll just hand it over to Kamlesh to take up your other question paper also.
Okay, guys, let's start with the next question paper. So, this was the end semester paper that we wrote, my batch 2024 to 25. Uh, so, let's go to the first question. First question was what is data? What are the challenges associated with data longevity and accessibility? Okay, so what is data? This is all available in your PPT. I think this is the first one, basic data science lecture one. So I just took it from that PPT as it is. So data is a collection of discrete or continuous values that conveys information. Example, the quantity, quality, fact, statistics, etc. So the key point here, the key points are emphasized in bold letters, as you can see. So these are the keywords that are expected from you in the answers. So you don't have to mug up and just vomit all the definitions as it is. It's not required. It is as far as the keywords are present, you will be getting the marks. So just keep that in your mind. And okay, the challenges associated with data longevity. So in your PPT there was only one point regarding this. So that is, there is no satisfactory solution for long-term storage of data over centuries or even for eternity. So basically there is no solution for long-term storage. That is what the challenge associated with the data longevity. And for data accessibility, there are 4 points. Uh, Much of scientific data is never published or deposited in data repositories. In a recent survey, data was requested from 5 and 6 studies. You don't need to write these numbers exactly as it is given in your PPT. You can just vaguely write that in recent surveys, uh, many like for example, just read this and understand what it is saying. So what this is saying is that from 5 and 6 studies, uh, only like less than 1 out of 5 of these studies were able to or willing to provide the requested data. So you can vaguely write it as in a recent study, it was found that 1 out of 5 publishing like publishers were interested in providing the requested data. So writing like this is more than enough. You don't need to memorize these numbers. This is important, this fair data. A solution to the problem of reproducibility is the attempt to require fair data. The abbreviation of fair is given here: findable, accessible, interoperable, and reusable. This is one of the important uh, topics in that entire like in that entire topic. Data that fulfills fair requirements can be used in subsequent research and thus advances science and technology. The next question: how is data typically classified? And what are the primary types of data classification? Data is typically classified in 3 ways, as you know: structured, unstructured, and semi-structured. Structured is generally in tabular format. The elements in structured data are addressable for effective analysis. Example table, database, etc. Notice that here example was not asked in the question, but then I am writing the example. It is important that you write examples and uh, if any if possible write draw diagrams for any question. And similarly in coding questions, it's prescribed that you write the outputs regardless whether it is asked or not in the question. Unstructured data does not follow any organized format or predefined standard, example Word, PDF, etc. Semi-structured is information that does not reside in a database but that have some organizational properties that makes it easier to analyze. Next question: what are the main objectives of data imputation and scaling? Data imputation refers to the process of filling in or sorry, filling in missing or incomplete values in a dataset with estimated substitutes rather than discarding the records. So suppose you have incomplete values in your dataset, rather than discarding it, the values, you can substitute those numbers with estimates. Main objectives: reduce bias. So this ensures that the models are not trained on incomplete or biased samples. For example, if you in the data set, if all the small values are missing, then uh, obviously the trained data is biased towards greater values, right? But then if you use data imputation techniques, it won't be as biased as discarding them altogether. That's how it reduces bias and maintains consistency. It keeps the data structure uniform, of course. Improves model accuracy because most of the models need complete data set, complete information, and they might not work as intended if there are missing information. That's why we are using imputation. Common techniques: simple imputation, replace with mean median mode. Second imputation uses similar instances to estimate missing values. The next one is feature scaling. Feature scaling adjusts the range and distribution of numerical data so that all features contribute equally to the model training. Main objectives: faster convergence. So when while you are training a model, if the features are not scaled properly, the convergence rate is slower. That means it has to go through many iterations in order to converge to a final least error state. But then if you scale it beforehand, you will get faster convergence. That's what is written here. Preserve relationships, keeps proportional differences between data points consistent, ensure algorithmic capability. As we saw in the previous imputation, this also is like similar. The algorithms that you are using, they assume that the data set that you are inputting is scaled properly. So they require this required scaled data sets. So you have to scale the data sets before you train a model. Enhance numerical stability, avoids overflow or underflow issues in computations. Common methods for scaling: normalization, standardization, and robust scaling. Min-max scaling is nothing, normalization is nothing but min-max scaling. So min-max scaling will rescale the feature to 0 to 1 range. And standardization is z-score normalization, z-score scaling. It centers the data such that the mean is 0 and standard deviation is 1. The next one is robust scaling, uses median and IQR to handle outliers. Okay, Tom Mitchell's definition was already covered by Harshini. So this is just the question repeated. So just know that this is an important definition because it got repeated twice. This is second time it's getting repeated. And what are the typical problems observed in unpreprocessed data sets? Okay, so if you, yeah, so in unpreprocessed data sets, of course, there are missing values. The formats might be inconsistent. For example, different units, different date formats, etc. And they are outlier prone, so there can be outliers because it's not scaled. Okay, then unscaled features, same. Categorical variables. So if you have text or something, some labels, the models cannot handle it directly. That's why you use encoders, one hot encoder, and so on. Those features to categorize the variables into numbers, into integers. It converts the text into integers such that the model can handle it. Duplicate records can be present, the data can be noisy, the classes are imbalanced. Imbalance meaning one class heavily outweighs others. So it means that one feature will affect the output more than all the other features. This can be reduced by scaling. Irrelevant or redundant features. So yeah, if you have so many features, then the model space becomes sparse, so leading to bias predictions. So you need to do feature selection using PCA, so that you just identify the most important features and train the model based on those features alone and not all the irrelevant features. Next question, second question, C part. Don't worry, I'll share this entire um, Notion workbook along with the previous year question paper itself for your reference. You can visit the questions after the live session. Okay. This question asks difference between fit and fit transform. So as we saw in the coding section, fit versus fit transform. Fit is only for learning the parameters from the data. Example, in standard scalar, learning parameters means learning the mean, getting the mean value, if the strategy is mean. Or in one hot encoder, it's the category. It does not change the data, just stores what it learned. So if it is fit on one data set and it is transformed on another data set, it does not use the second data set's mean. Rather, it uses the first data set's mean on which it was fitted. That's why that's the difference between fit and fit transform. So transform uses the learned parameters to transform data. All these we already saw in the code. Train scaled is basically scalar dot transform of X train. X train is the training data set. You transform the training data set based on the scalar. The scalar was fitted on the X train. I'm sorry. Yeah, transforming X test also. Okay, I'll just repeat this concept once again. You are creating a scalar method object, and you are fitting the scalar object using the X train dataset. That's the training dataset. So the scalar is fitted, that means trained on the training dataset, and then scalar dot transform X train, scalar dot transform X test. So you are transforming training X train dataset and X test dataset based on what you fitted using X train. So it uses the same mean values that were present in the X train to transform for X train and X test. And you are just storing these in different variables. Whereas in the other hand, this is fit transform. Fit transform is the convenience combo for fit and then transform on the same data set. So instead of writing two lines for first fitting and then transforming here, you can just write a single line standard scalar dot fit transform of X train. So it will fit the model based on X train and transform the model and transform the X train data itself, and then returns the final output to X train scaled. That's it. So next, the next subdivision in this question itself, features of naive Bayes classifier. It is based on Bayes theorem with an assumption of independence between features. So features must be independent. That's one of the assumption of naive Bayes. and it is simple and fast to train and predict, works well on text classification and categorical data, performs well even with small data sets. This is one of the main feature of naive Bayes classifier, and it can handle multiple classes easily. These are the features of naive Bayes. Okay, 3a. Write the code to fit simple imputer to this data and transform this data. Calculate the output. That's it. And define multicollinearity. This is the next subdivision of the same question. If you remember, we did this exact code sometime before in the Colab notebook. It was the same question. So I'll just reiterate again. That's not an issue. So first we are importing the necessary libraries, creating the data, creating the simple imputer using this line. Imp equals to simple imputer, strategy equals to mean. Fit this imputer on X. So we are fitting it on X. X was given in the question. And then transforming. So new data. New data is also given on the question. In this question. Here. This data. So whatever the simple imputer learned from this data, we are going to use that learning and apply it on the new data. Output equals to transform of new data. So this will apply the knowledge that the imputer has on the new data, and then returns the output, and then we are printing the output. This is the code, and I forgot to include the sample output also for this, but then in your exam be make sure that you write the sample output also. Wait, okay, never mind, I included the sample output myself. So if you want, I'll show you the working also. So this is the data on which the simple imputer was fitted on. This data is given here. From this, mean is 1, 3.4, 10. The sum of this by 3. 1, 3.4 and 10 are in this column, the first column. Make sure that you include the numbers in the first column wise. So the mean is 4.8, and similarly for the second column 1.2 and 5. The mean is 3.1, and for third column the mean is 5.63. So these are the mean for each column. Now we are applying the transformation on the new data, this one. So here in the first column we have np.nan. So we replace this np.nan with the mean of the first column 4.8, and similarly the second column we have 2 np.nan. So we replace both these using the mean that we obtained for the second column, that is 3.1. So after applying, this is the final output. Here we got 4.8, here we got 3.1. This is the final output. And the next subdivision of the same question, multicollinearity. Multicollinearity occurs when two or more independent variables in a dataset are highly correlated with each other. It causes unstable regression coefficients. As we saw earlier in the ridge regression part, the regression coefficients will be unstable because the standard errors obtained will be large. The coefficients may change signs or magnitude drastically with small data changes. So as we saw earlier, it gets more sensitive to the data set. So very small changes also may change the signs or magnitudes drastically. This happens during multicollinearity. It reduces interpretability of linear models uh, solved by dropping correlated features. Okay, so this was the problem that we saw. This can be solved by dropping the correlated features, or I mean using PCA, or applying regularization, ridge regression, as we saw earlier. So this is the next question. Okay, so this was also covered previously in our collab coding time section. So you can find the code for this in the collab notebook that we are going to share with you. The code is here also, like given here also. I hope we can skip through all these codes because we have seen this multiple times. I'll just explain the formula for this and how this is being calculated for like calculating the output alone. So, okay. First step, this is the data set. We have to find the maximum absolute value in each column. So in this column it is 2, in this column it is 1, in this column it is 2 again. So we made a note of that, and then we are dividing each column by its absolute max value. I mean max absolute value that we found in the last step. So okay, get to the first column, 1, and the max absolute value is 2. So the first, this entry becomes 1 by 2. This entry becomes 2 by 2, which is 1, and this entry becomes 0 by 2, which is 0. Similarly, moving on to the next column. For this column, the max absolute value was 1. So it's basically the same as writing down the same column as it is. And for this column, max absolute value was 2. So this will be replaced by 2 by 2, which is 1. And this is 0 by 2. And this is minus 1 by 2. So after replacing everything, this is the final output that we get. This was max upscaler, and you can note that the range is from -1 to 1. Next question, how do kernel functions enable SVMs to handle non-linearly separable data? So as you would have learnt in SVMs, there are two kinds of SVMs. One is linear and another is non-linear. So non-linear SVMs uses some functions called as kernel functions. These kernel functions will transform the data, input data, into a higher dimensional feature space where the data points can be linearly separated. For example, if you are given a 2D data set, uh, the kernel function will transform the 2D data set into a 3-dimensional data set, and it checks whether the data points can be linearly separated. If it can be linearly separated, then a linear SVM is used to locate the nonlinear decision boundary in this modified space. So kernel functions is the key to handle non-linearly separable data, because those are the functions that help us to transform the non-linearly separable data into a higher dimensional feature space where the data points can be linearly separated. Next question. Drawn explained a single layer perceptron provide mathematical function used in its operation. This was directly taken from your PPT, I mean your PDF that was present for you in your material. It is enough if you just directly draw this neuron. So this is a single layer perceptron, right? And provide mathematical functions. So these are the mathematical functions here present, written here. So it just says that y equals to 1 if sigma weight I into xi is greater than or equal to 0. What this says is that weight I is given here. Weight 1, weight 2, weight 3, weight 4 till weight n, and x1, x2, x3, so on till xn. So you have to write the product sum of products of all these and check whether it is greater than or equal to 0. If it is greater than or equal to 0, y will be 1, else it is 0. in the other case. Okay, and this is one accepted convention. Here we saw that like the threshold is we are setting it as 0, but then in general it is set to be theta. Theta is a threshold. So if it is greater than that particular threshold, this y will be 1, else it will be 0. This is basically a single layer perceptron. This is how it works. Yeah. Let's move on to the next question. Okay, consider the function given below. Is this a valid probability density function? If so, determine the probability that the variable falls in the interval is 1 comma 2. Okay, let's first solve the first subdivision. First, we have to check whether this is a valid probability density function. For checking that, we have to check whether f of x is always positive or like greater than or equal to 0 for all x. That's the first step. Here it is true because in no case it can become f of x can never become less than 0. So you have to write that this formula, like this condition holds true here. And then the other criteria to check is the total area under the curve is 1. So you have to integrate the given function from minus infinity to infinity and check whether it is coming out to be 1. So this is the computation part of that. This is all just basic integrals. You'll know all these by now. So yeah, these two conditions were satisfied. So we can conclude that this is a valid PDF. Next part, we have to find the probability that the variable falls in the intervals 1 to 2 with 1 and 2 not included. So we are, so basically we are integrating this function from 1 to 2. And then that gives us the answer. This is the answer after integration. I hope you will know to solve integrals, so that's not a problem. This is directly the answer. And the next question was CDF at x equals to 2. CDF means starting from 0 till some x value. It is the cumulative density function, right? So we have to integrate from 0 till 2. So integrating from 0 till 2 will give us this value. This was the question. So yeah, moving on to the next question. What are the assumptions of naive Bayes algorithm? Assumption. Oh wait, this was already like this already came, right? So this is basically the same answer as before. Moving on to the next question. Define two types of random variables with examples. What is CDF? So the two types of random variables are discrete and continuous. Discrete random variables take countable distinct values. It may be finite or infinite. For example, number of heads in three coin tosses 0, 1, 2, 3. Continuous random variable takes any value within an interval. It is uncountable. Example, height of a person, time taken to finish a task, etc. And what is CDF? CDF is the uh, CDF of a random variable x gives the probability that x is less than or equal to a certain value x. To find that, you have to integrate from minus infinity till x. In discrete variables, it is summation p of x equals to t, where t is less than or equal to x. So this is just an example of CDF. So yeah, this function f of x equal to e power minus x, where x greater than or equal to 0, then f of x equals to 1 minus e power minus x. So if you substitute x to be 1 or 2 or any number for that matter, you get the CDF directly. Okay, the next question is draw McCulloch-Pitts neuron. Illustrate with the graph showing the relationship between model complexity and error. Okay, this is separate and this is separate. These are both the subdivisions of the same question. First part, McCulloch-Pitts neuron. This is basically the neuron that is given in your PPT. You can just have a look in that. So this neuron takes inputs from like multiple inputs, n inputs, and then outputs a y value that is in the like that is either a 0 or 1. I hope I don't need to explain McCulloch-Pitts neuron. It's since it's straightforward. The next subdivision is model complexity versus error. So okay, model complexity. X-axis represents model complexity. Y-axis represents the error. This error is often calculated using the ordinary least squares or some similar methods, L1 error, L2 error, like that. So as the complexity of the model increases, you can notice two things. First thing, there is some irreducible error that cannot be reduced ever. So it is constant. And then there is training error. So as the model complexity increases, you can see that the training error keeps on decreasing, because that's the point of making the model more complex, right? You want to reduce the error, so you make the model more complex. You train it using more examples. You fit the model better. So that reduces the training error. But in the other hand, the variance will increase as you increase the model complexity. This is the key part about the bias variance trade-off. You can see that the bias is reducing over time as the model gets complex, more and more complex. But then as the bias is reducing, you can see the variance is increasing. So you can infer that when one increases, the other will decrease. So you have to find a sweet spot that is the best for like that is neither underfitting nor overfitting. We call it underfitting zone when the bias is large, and if the variance is large, we call it the overfitting zone. So we need to find a zone that is neither underfitting nor overfitting. Such a zone is this zone. Yeah, that is it. So you have to draw this graph and then explain about the underfitting and overfitting, and then finding a balance between the bias and variance. That is all that is expected from you in this question. The next subdivision, how ridge regression helps in reducing mean square error. This we have seen multiple times. So first tell about the problem. What problem you have. When multicollinearity is there, it becomes unstable. Small data changes causes large swings in coefficients. So start with the problem and then tell the solution. The solution here is ridge regression. So ridge regression adds a penalty term, which is L2 regularization. This is the cost. You don't need to like if this equation is not there in your PPT, you don't need to learn this. Just go through with whatever is there in your PPT. I think it is even enough to just write this line. This line tells about the ridge regression entirely. This summarizes the entire ridge regression in one single line simply. So this is what is expected from you. And effect on model. So the penalty term shrinks large coefficients towards 0, reduces model variance, and thereby reducing overfitting while adding a small bias. So we are increasing the bias in order to reduce overfitting. And the trade-off often results in lower total error, bias square plus variance, thus reducing the test MSE. Okay, the next question is ordinal encoder to provide to encode the matrix. This matrix, I think we have covered the same question already in the coding section, so I am skipping it for now. I'm skipping the code, but then I'm explaining you the sample output how it came. So an ordinal encoder, we encode it in numeric. I mean, the numeric values are encoded based on the ascending order, and then the text are encoded based on the ASCII value. So f comes before m, so f gets encoded to 0, and 1 2 3 are encoded as 0 1 2 respectively. After you encode all these, you can just replace females with 0, males with 1 here in this array. So that will help you to arrive in the expected output. That's it. Okay. The next question. The diagrams explain homoscedasticity, heteroscedasticity. This is arguably one of the most important concepts in this chapter. So the heteroscedasticity and homoscedasticity, you need to know to draw the graph and then explain the difference between these. This is a short question in your exam. So as I said earlier, heteroscedasticity is when the x-axis is basically the predictor variables. Remember the x labels. So as the inputs, x is basically the input, right? So as you get more and more inputs, you can see that the variance, the spread, is getting increasing in the in the graph. So here the spread was less, and as we go towards the right side, the spread is getting increasing. The spread is increasing, that means the variance is also increasing. But in homoscedasticity, it is not the case. As we go towards the right side in the x-axis, the variance is not increasing. It is almost the constant toward, throughout the entire region. This is the main difference between homoscedasticity and heteroscedasticity. So yeah, definition, variance of errors is constant across all levels of the independent variables. Here it changes. Graph pattern, points are evenly spread, points are cone shape. You can write this cone shape. Variance widens or narrows. Effect on regression, valid standard errors and reliable significance test. Remember, this was one of the assumptions of linear regression. We assumed that the data is homoscedasticity. So if the data set is homoscedastic, the model train will produce reliable outputs. That is not the case with heteroscedasticity. And examples, predicting height from age in adults. So if you predict take the data set of adults, it is more or less the same, with the same variance, right? But then predicting income from age, predicting income from age, variability grows with age. So as the age gets increasing, the difference between the salary will also increase, right? Someone at 21, the age of 20s, will all the people at the age of 20s, like they get the somewhat similar salary. But as the age increases, suppose at 60 years of age, one might be still stuck at getting some 1 lakh per month, but then a few outliers, I won't say outliers, but then a few other people might be getting more than like 5 lakhs, 10 lakhs per month. So that variance, that difference increases as the age increases. So this is one good example. That's it. Let's move to the next question. In 256 sets of 12 coin tosses, how many outcomes are expected to have exactly 4 tails and 8 heads? Okay, so uh, you might not be aware of this distribution, but this distribution is called binomial distribution. Here, binomial distribution like takes place, can be applied when there are two possible events. Here it is either tail or head, right? So this is the formula for binomial distribution. P of x equal to 4. We are assuming x equal to like head is equal to x. So we want x equals to 4, because if we take x equals to 4, then it automatically means that there are 8 tails. So there it is enough if we take one, either head or tails. So here I am taking heads. So p of x equals to 4 equals to, this is the formula, 12c4 into 0.5 power 4 into 0.5 power 8. Here 0.5 power 4, this 4 corresponds to the number of heads and this 8 corresponds to the number of tails. So applying this formula, you will get the answer to be 0.1208. So it is just enough if you know this formula. That is all that you need to solve this question. And expected number of such outcomes in 256 sets. So remember, this is only for one particular set. So you are repeating 256 times the same thing. So you have to multiply this number into 256. That will give you the expected number of such outcomes. So just multiplying 256 into 0.1208, that will basically give you 30.9375. This means that roughly 31 times in 256 sets, this situation is possible. You can get 4 heads and 8 tails in roughly 30 times out of 256 times trials. That's the expected number. That's it. The next question. I think this is the last. Okay, there are two more questions. Define homoscedasticity and heteroscedasticity with diagrams. This is already repeated. We just covered it some time before. Next question. Define supervised, unsupervised reinforcement learning. Provide examples for each. This is just directly from your PPTs. It's a straightforward question. So you have to uh, write the formal definition for supervised learning. Again, I have emphasized the important keywords with bold letters here. So make sure that you don't miss those keywords. And examples: support vector machine, SVM, linear regression, logistic regression, etc. Unsupervised learning, here's the definition. Examples: clustering, k-means clustering, etc. Reinforcement learning, definition is given. And example is Q learning and DQN. You can write chess learning bots, Go learning bots, like that. There are multiple reinforcement learning algorithms. Okay, the next question is, list the typical steps involved in implementing a supervised learning model. Again, this is also uh, the same, like this is directly asked from your PPT. So it is enough that you write the points given in your PPT. Again, I am reiterating, um, go through your PPTs multiple times, revise each and every slide. Whatever is asked in your exam will definitely be directly from your PPT, except a few numericals and code questions. What are the major next question? What are the major challenges encountered in supervised learning? So I think you would have covered this also. So first one is bias variance trade-off, as we saw earlier. There is underfitting zone, overfitting zone. You have to find a sweet spot between those. And function complexity versus data. So if you have a simple function for small data, it works. But then a complex function for a small data won't work good, because there are more chances that it overfits to the data, because the data is very simple, but then the function you are using is very complex. So it can occur that it only corresponds to that particular training set, resulting in a underfitting. So that's what this says. So you have to find a balance between the function complexity and the data. The next point is dimensionality. High dimensions leads to more confusion, leads to high variance. So as I already said, this can be eliminated using feature selection. When you have high dimensions, what is high dimension? High dimension basically means having many features. Okay, dimensions can corresponds to features. So when you have less data, I mean less rows in your data set, but then many columns, that is features, that means the variance is high. So you need feature selection to select the most important features and discard all the other features. For this you use PCA. And another challenge is noise in output. Uh, Noise in output basically means, yeah, so your input is always, like your input always has noise. So when you have noise in your input, there are high chances that you have noise in your output also, right? So you have to fit, I mean, do pre-processing beforehand such that your output efficiency is good. And at the same time, you have to also like ensure that you don't overfit the data. Yeah, again, the same diagram. Okay, the next question is mathematical formulation for simple linear regression. Simple linear regression is basically y equals to x beta plus eta. I mean epsilon, where epsilon is the error term, beta is the coefficient vector, x is the design matrix, that is the matrix of the independent variables, the x variables, and y is the response matrix, that is dependent variable. And these are all given here. These are all matrices, by the way. So the X matrix includes all the intercept columns. I mean, wait. Yeah. So make sure that X contains the first column as all ones. So in X, if you see in the PPT that was given to you, the first column was 1. All the rows are filled with ones, and then the subsequent columns are your feature columns that are in your input data set. And in the beta matrix, you can find that beta 0 is the intercept, and beta 1, beta 2, etc. are the slopes for the line that you are drawing. So if you are asked the mathematical formulation, you can just write this simply and then explain what each term means. That's it. Next question. Define and differentiate between accuracy, precision, recall with examples. Again, the definitions are all given here. You can refer to them. You would have already studied them a number of times, so I am skipping it. And make sure that you learn one example for each of the accuracy, recall and precision, so that you don't need to create your own example in the question paper when you are asked in the exam. So make sure that you look uh, look into one example beforehand. Moving on to the final question of the day. Explain the working principles of KNN for both classification and regression tasks. So in KNN classification, the output is a class membership, as you know. So you basically get the input data and then classify whether it belongs to a certain class or not. An object is classified by plurality vote of its neighbors, with the object being assigned to the class most common along its k nearest neighbors. And k is the hyperparameter that you are setting. So k equals to 1 means the object is simply assigned to the class of that single nearest neighbor. So I hope you understood what KNN classification is and how it works. So it first finds its k nearest neighbors, and then depending on the k nearest neighbors, it determines the class of the unknown data point. In K-NN regression, the output is a property value of the object. So, for example, if k equals to 1, the output is simply assigned to the value of that single nearest neighbor. So when we were writing code, we wrote a code for KNN regression also. KNN regression also. If you remember, what we did was we found out the nearest two neighbors and then took the mean of those two neighbors for that particular column, and then we imputed in KNN imputer. So that's how KNN regression works. And both for classification and regression, a useful technique can be to assign weights to contributions of the neighbors. This is a bit advanced, but yeah, you can assign weights to the contribution of the neighbors. For example, suppose you are assigning the weights in such a way that the nearest neighbors contribute more than the neighbors that are far away. This way, you can improve the model's performance. A common weighting scheme is weight is equal to 1 by d, where d is the distance of the neighbor. Yes, so that's it, guys. We are done, officially done with the questions for the day. Now, I'll pass on to Harshini for presenting the tricky questions that we have prepared. We won't be covering this in detail. We are just going to show it to you and then give it to you in the description box. You can cover those questions as per you, please, when you get time.
Okay. So now we'll just look at a few tricky questions that we had come across during our in-semester, mid-semester exams. So the first one is basically just comparing between your violin and box plot in terms of your modes of distribution. Now, I think when I started with just explaining the concepts that you guys had asked, we had come across this particular graph that's like basically just for box plot that represents bimodal, uniform, and normal distribution. But I don't think there was a graph for your violin plot. So now over here you can see how your normal distribution looks like. It has that normal shape of your box plot and then that bell-shaped curve for your violin plot. For a uniform distribution, this represents the flatness of the curve and it's like rectangular in shape for your violin plot. For your bimodal graph, you can see that two peaks are showing up. So it represents, so the number of peaks in your violin plot basically represents the modes that are present in your data. So if you draw this and just explain whatever I've said, that should gain you the mark. And this we have seen. The feature selection methods also we had seen with respect to your diagrams and your cross validation sets also. And your feature selection methods also we had seen with respect to filter based and wrapper based. So I'll just skip that. Mathematical problems, this, okay, another thing that I wanted to address was there's probably a PPT that was shared with you for probability distribution. So just make sure that you try out every sum that is present in there because down to the numerical value that was in that PPT, it has come as it is in your question paper. So it's better you don't risk it and just solve it. At least see how to solve it. It would have been easier if you guys had some background knowledge on statistical and probability course, but at least that particular PPT covers every type of question that could show up in your exam. So ensure that you solve everything because this question showed up in our mid semester and it is the same thing except the value was changed. Over here, they say that there are three cities A, B, and C, which are like equidistant to each other. So we'll assume that the distance between each of them is T. I mean D. So your cyclist travels from A to B at 50 kilometer per hour, B to C at 34 kilometer per hour, C to A at 16 kilometer per hour. So we need to find the average speed in kilometer per hour. So first, you need to find total distance. After that, you need to find your total time for getting average speed. Do not average all of these speeds and provide the average of that. That would lead to a wrong answer. So for each pair, we're going to take your distance as d kilometer and the speed corresponding to each stretch, that is A to B, B to C, and C to A, is written as given as follows. So the whole A to C stretch is basically d plus d plus d, which is 3d. And what we're going to do is we are going to take the total time because now we have the total distance that is 3d. Now we need the total time. So time is nothing but your distance by your speed. So with respect to that, we'll calculate for each stretch and we'll sum it up. So for the stretch A to B, it's d by 50, and then for B to C, it's d by 34. To C to A, it is d by 16. Find the LCM and get P is equal to this particular value. Next thing, you just divide it and you get something like which is equivalent to 26.8 kilometers per hour, which is not present in any of the options. So the correct answer is none of these. Moving on to the next question, the coin toss question. Again, this was there in one of our papers, but this requires knowledge of your binomial distribution. So we just need to ensure that you take one of these that is exactly x is equal to 4 and then perform that calculations accordingly. This particular question is there in your PPT. So go through it and it was also there in that in some paper that was explained just now. And the remaining, all of these questions we have covered in our code segment. So just refer to the code segment for the answer and the output. How do you write it down? And when we had discussed the previous year questions, me and Kamlesh, we have, you know, briefed you about how to write it step by step. So follow that, and marks are guaranteed. And another thing that we hadn't covered was your output prediction, just asking what could be the output for this particular code. And this will be attached in your Google Colabs. Another thing that comes up really frequently is your homoscedasticity versus heteroscedasticity, your ridge regression and your model complexity. Under that, you get your ridge regression, how it helps to reduce your mean squared error. And if you have to draw with respect to your deep learning concepts, your McCulloch neuron also shows up with respect to your perceptron also. So these are the two main concepts. How to illustrate them in graphs was also mentioned by Kamlesh when he was explaining his segment. And I think that's it. Wait, okay, there are, you need to write the definitions for entropy and Gini impurity in context of decision trees also. So just mention it as it is in your PPTs and you will be done. So with this, we have covered whatever we've promised to cover. That is whatever we told that we would do, starting from the concept that you guys had requested us. Then we solved two whole end semester papers worth 3 hours in a short span of time, with how to approach each question and which diagram to use where. After which we have taken up the tricky exam questions and we've put it into a PDF so that you guys can refer it anytime that you want. We'll also be sending out a few test yourself questions that you can use to practice, because now you guys are exposed to all the type of questions that have come in your previous batches also. So this is just something that are kind of similar, but they're not the same as to what we've discussed. So just go through that and you guys should be fine. We'll share all of these details in your description box in one particular drive folder. All of these will be accessible, so you can use it when you're revising. And if you have any doubts, just put it across in that digital space link that we'll be sending. So I think that concludes our session. Kamlesh, do you have anything to say to them?
Yeah. So all the very best, guys. Yeah. So we have done as much as we could, and I hope you would have prepared very well. So yeah, I don't have anything else to say. If you have any doubts, you can put it in the live section, live chat. We'll wait for a minute or two. If we have any doubts, we'll address it, or else we'll just find out. Thank you for staying with us until now. Thank you.
Okay, guys, there were no doubts, so we'll just be wrapping up this session. I hope this was really informative and it helped you in some way because we kind of spent a lot of time to ensure that you guys get quality content. And all the best for your exam. Me and like we all have faith in you, like the whole YTS group. We are rooting for you guys. Ace it, and we'll see you guys in the upcoming videos. Thank you.